The Cretaceous period. It's just loaded. It's a star-studded gala of cool geographies, active tectonics, and whacked out life forms. In terms of the geography of North America, we'll see the North American Interior Seaway. How cool is that? And in that seaway are sediments, including those of the Mancus Shale. It's one of Dr. Bob's top 5 favorite rock formation, the Mancus. Silvery gray, intricately weathered appearance. That's in southern Utah there near a place called Hanksville. And around that seaway were life forms, much like these. Dromaeosaurs called Velociraptor. Indeed, these are from one of the earlier Jurassic Park films, where they were depicted as featherless. In fact, now we think velociraptors sported feathers. So our ideas are changing. But with all of that would come the end of the Cretaceous, and it would be an end of the dinosaurs. The Cretaceous period is the third and final period of the Mesozoic era, and it spans a range of 145 to 66 million. So we are getting right down to the end of Earth's timeline. Here is the ICS time chart showing the Cretaceous, and it's split into lower and upper. It's got a bunch of different epochs there. The only one that we see more than the others is the Maastrichtian, and that's a European term. And the reason it gets so much press is it's the one right there at the boundary. And so when we talk about the KT mass extinction, K for Cretaceous is the map symbol, T for Tertiary, which is the next period after the Cretaceous. The KT boundary there is right at 66. So the Maastrichtian is the epoch just before the end of the Cretaceous. These rocks are named for formations in Western Europe, specifically the chalky sedimentary rocks of southern England, the White Cliffs of Dover. When we look at northwestern Europe in terms of what it used to be back in the Maastrichtian, see the term there? So that means right at the end of the Cretaceous, Maastrichtian. So that means that this map represents a time period somewhere between 72 million and 66 million. So shallow seas covered much of northwestern Europe, northern Germany and France and England. So these sediments deposited in this ocean are now exposed as the White Cliffs of Dover. Geography of the Cretaceous. Let's take a look. Here's a picture of what the late Cretaceous looked like at about 69 million. Notice that the rifting of Pangaea is complete. The North Atlantic and the South Atlantic have both formed, the North Atlantic widening. The South Atlantic has opened up as well, although it forms more of a seaway than a broad ocean basin at this point. They are interconnected though. And notice the Tethys Seaway is shrinking. This subduction zone relentlessly getting rid of oceanic crust here, bringing the Indian Plate and the Australian closer and closer with time until they'll finally collide later. So the seaway there that is the Tethys is shrinking. There is still a passageway between the Western Hemisphere and the Eastern Hemisphere in terms of oceanic circulation. So you can still sail a boat around the world along the equator. This is a time of high sea level. The climate was warm, and it would continue to be warm right through the end. And there's some other factors involved too that are raising sea levels. And what we will see is marine transgression and the sea moving up on top of the cratons, on top of the continents, and we'll get inland seas or cratonic seas, interior seas. There are different names. And a famous one is this North American Interior Seaway, which would stretch from the Gulf of Mexico north towards the Arctic. Let's look at Ron Blakey's paleo globes, and here are the reconstructions for the early Cretaceous about 120. the Western Hemisphere here, you can see North America, the Gulf of Mexico prominent, Foreland Basin Ocean there in the north. South America and Africa starting to rift apart. Eventually they'll succeed, but for now they're still tied together there. Still a seaway in between the southern continents and the northern continents. In the eastern hemisphere, the Tethys Ocean is fairly broad, with subduction zone along the northern margin there. India would be down here, and with subduction of this plate, it will move farther north. As we move forward in time to about 105, broad Cratonic Sea, North America, Gulf of Mexico, not a whole lot changed there, but in the south, we do have a completed rifting event separating South America from Africa. So a very narrow seaway, around 105 million. In the eastern hemisphere, Tethys is still there. So let's play it back a little bit. So early Cretaceous, middle Cretaceous. So really it's this right here we're looking at in the western hemisphere. The creation of the South Atlantic Seaway. In the eastern hemisphere, the narrowing of the Tethys Ocean Basin slightly. You can see India moving north a little bit. As I mentioned, there's so much going on now that Dr. Blakey had to use 3 globes to actually showcase the later part of the Cretaceous. So this is around 90 million. If we look at the hemisphere with North America, you can see the full-blown North American Seaway, mountain range off to the west, going from the Arctic all the way to the equator, broad Cratonic plains here. The whole Craton has 3 separate geographic areas: a western mountain range, kind of north-south, a broad set of continental plains in the east, and they're both separated by this relatively shallow ocean in between. That's a geography that I don't know that Earth has ever seen, and we haven't seen it since. And it's one of my favorite geographic landscapes of the past. So you can see the rifting now of South America and Africa continuing. Off in the European area here, the Tethys is really narrowing down. A lot of scraps are starting to converge between Africa and Eurasia. This is more or less a continent-continent collision getting ready to happen, and the mountain range that'll occur as a result is the Alps. And then farther off in the eastern hemisphere here, the Tethys view, it is narrowing again with India down here, making its way north. If we move now into the end of the Cretaceous, the latest Cretaceous at 66, right there at the KT boundary. So K for Cretaceous, T for Tertiary. This is the picture. Again, North and South America still separated. They wouldn't come together until very late in the Cenozoic. So oceanic circulation existed between the Pacific and the Atlantic. The South Atlantic is widening, as is the North Atlantic. The collision between Africa and Western Eurasia is imminent. The Tethys is really closing here in the Eastern Hemisphere as well. See India moving even farther north. And when it eventually collides, it'll create a subcontinent-continent collision, and the mountains there that are going to form the Himalaya. So looking back, the late Cretaceous about 90, and then the latest Cretaceous right there at the boundary at 66. Notice North America, the seas will drain off by the end of the period. South Atlantic will grow. In Europe, the collision zone between Africa and Eurasia will narrow, as will the Tethys. And the Tethys itself in the Eastern Hemisphere do the same as India works its way farther north. So this oceanic plate here is subducting underneath Eurasia. Let's focus in on North America's geography during the Cretaceous. And again, Ron Blakey has provided a number of different time slices of this region. Here is the early Cretaceous, about 140. Cretaceous begins at 145. This is right at the beginning. We can see that the North Atlantic is opened here, the South Atlantic not so much. The Gulf of Mexico is right here. The western margin is mountainous. We had the Nevada and orogeny before, and now we're going to get two more during the Cretaceous. So mountainous west, you can see these island arc sequences coming in from the west, colliding with North America. So that's about 140. If we move forward 115, you can see a foreland basin developing here, stretching in from the north all the way towards the Gulf of Mexico. So a mountainous area here to the west of that, and a low, broad continental plain here off to the east. These highlands here will be the result of a subduction-related orogeny that occurred during much of the Cretaceous here. Foreland Basin Sea, very shallow. Again, there's the North Atlantic. As we move forward to the late Cretaceous at about 100, there's the Foreland Basin again, and it would come and go slightly as sea levels would change, and mountainous highlands off to the west. We're starting to see a little bit of rifting and separation here between South America and Africa. Late Cretaceous about 85, the full-blown connection of the Arctic Ocean with the Gulf of Mexico and what is known as the North American Interior Seaway, which is again a very cool geographic setting with mountainous terrain off to the west. Huge open ocean here, which is the Pacific. Mountainous region here off to the west of the North American Interior Seaway. And then on the eastern side, it's a broad, featureless, more or less, continental plain. And then at about 75, very similar. And right to the end at 66, that seaway would drain off. We're left with the mountains here, which are forming from the latest compressional subduction-related orogeny, and this is the formation of the Rocky Mountains, stretching all the way from Mexico through the United States into Canada. So let's look at the sequence. From early Cretaceous at 140 comes the seaway, 115, and the development of the North American Interior Seaway, about 85, and then as it drains off right at the end. So this is the geography at 66, where the last dinosaurs were present. One last note, just looking at these time slices, remember it's in this landscape where all the cool life forms of the Cretaceous, all the dinosaurs, pterosaurs, marine reptiles exist across this landscape and in these seaways. These shallow seaways were filled with marine reptiles. The margins along the shoreline there were probably flush with vegetation and had abundant land animals, dinosaurs of all sorts of kinds. Around the seaway was the dinosaur life that we are going to talk about, and in the seaway are the marine reptiles. So when you see this North American Interior Seaway, that is the home for a lot of these cool and exotic marine reptile forms. And this mountainous terrain and this Cretonic plain were the homes for all sorts of different dinosaurs. So the geography of western North America. During the first part of the Cretaceous, the severe highlands were the mountains that were forming on the western margins. And again, a subduction-related orogeny with a subduction zone here and collision between the oceanic plate to the west and the North American continental plate, giving you thrust faulting, folding, a continental arc which would stretch north to south along this margin. We see structures that represent this mountain range in Nevada today, the Keystone Thrust. Right here in Nevada, see the color separation between the dark gray rocks on the left and the tan rocks on the right. So this is a place called the Severe Fold and Thrust Belt. Right, and these are Cambrian rocks that are older, sitting on top of younger Mesozoic sandstones here, and so you can get older on top of younger like this because of the thrust fault. It's taking rocks that are down below and they're older and tectonically and placing them on top. So these would have been the severe mountains off to the west. To the east of those mountains, a broad plain with stream drainage, with channels and floodplains very broad in extent. A lot of continental sedimentation, fluvial sedimentation, rivers, streams. You'll get lakes in there as well. This is a cross section across this whole area from west to east, showing the severe highlands, continental arc, also tectonics, the thrust faults, so like the Keystone Thrust. And as that material gets loaded up on to the side of North America, it weighs the plate down and you get a broad warp called the Foreland Basin. And there's sediments deposited in that basin. And if it's deep enough, the sea will come in and form a Foreland Basin sea, which then would shallow off to the east. Off to the east of these mountains, eventually the ocean would transgress in and form a Foreland Basin seaway. Well, into the late Cretaceous, we would get the Western Interior Seaway. Geographic picture here, the severe highlands are now very wide. The orogeny is in full-blown development here, so the continental arc volcanoes exist, as do mountains that are tectonic in origin with all the thrusting and folding. A twofer, much like the Andes are today. So not just a volcanic set of mountains, but also tectonic. East of that is the Western Interior Seaway, which is now connecting the Arctic with the Gulf of Mexico. Here is a broader picture of it where you can see its true extent. And they actually give some names to the land areas, Waramidia maybe, and Appalachia off to the east. A narrow seaway, fairly shallow, that is extending north to south across the North American Craton. There is T-Rex in the late Cretaceous, just for a stroll out on the beach on the western side of the seaway. Another feature a little closer to home, farther down here in Arizona, is something called the Mogollon Highlands. And this just represents the mountainous area of this continental arc present right across the southwestern part of the state. And so volcanic mountains were down there in the Yuma area. The foothills of those would extend towards Phoenix. So this broad area of southern and central Arizona was not just the arc, but there's an uplift here called the Mogollon Highlands. So this whole region down here was high, and this area to the north was low. Okay, so not just the volcanoes here, but this kind of Mogollon Highlands area. And from those areas would drain streams carrying sediment off towards the ocean in the north and off to the east. The Mogollon Highlands. This topography here is totally opposite of what it is today. In the Cretaceous, it was higher in the south, lower in the north in Arizona. As you know, now it's lower in the south. As you go north, it gets higher. Later in the Cretaceous, the geography would include the Rocky Mountains, which are forming by about 80 million, and they'll last through the end of the Cretaceous. So this subduction-related tectonic activity producing first the severe orogeny and the severe highlands are now forming the Laramide orogeny in the Rocky Mountains. Here is the picture of the open ocean to the west of the Pacific, the shallow interior seaway here, the North American Interior Seaway, and the mountainous region in between, here called Laramidia. That's where the severe highlands were, and now the Rocky Mountains will begin to form here. These mountains will start to form basically in areas where there were never really mountains. In fact, the ancestral Rockies were the only other place in this part of the Craton that experienced any kind of mountain building. It's a return of the Rockies, and that is a story we're going to be talking about through the Cretaceous. The seaway itself is going to drain off eventually by the end of the period, and as the Rockies rise, seas will drain away. And so this is kind of the final Phanerozoic marine regression. The seas came up and down a lot during the Paleozoic and Mesozoic, but they're finally reached their high point, and now they're lowering and draining off. So the shorelines are moving seaward. So this might be Laramidia here and the shorelines of it, and there's the North American Interior Seaway. Pretty cool. Well, if you like tectonics, this will be right up your alley. In the early Cretaceous, we look at the diagram of Earth, and it shows in red the rift zones and mid-ocean ridges. Here's the mid-ocean ridge in the Pacific that is creating the Pacific plate on the west side and the Farallon plate on the east side. Okay, so a similar mid-ocean ridge in the Tethys, creating the Tethys oceanic plate. A mid-ocean ridge is creating the North Atlantic Ocean basin here, and starting to progress into South America and Africa. So rifting is going on. That's a major process that continues, this rifting and widening of the North Atlantic, and now the South Atlantic starting as well. The other side of the coin are these collisional orogenies, where you have plates colliding. Like I mentioned, this Farallon plate here is subducting underneath North America to produce a subduction-related orogeny known as the severe orogeny, and all the highlands and folds and thrusts and volcanoes that come with it. Same is occurring in South America, and that'd be the Andean orogeny, forming the Andes. We have orogenies also in Southeast Asia that are similar, subduction-related, as the Tethys plate subducts underneath Eurasia. So both extensional tectonics and rifting and compressional tectonics are both very prevalent during the early part of the Cretaceous. Did I mention rifting was going on in the Cretaceous? I think I did. All over the planet, we had extensional tectonics or rifting. In the northern hemisphere, finally the separation of the North American plate and the Eurasian plate. The spreading of the North Atlantic will progress northward and produce a separation between North America and Eurasia. Rifting will also progress to the south, forming the South Atlantic Seaway, separating South America from Africa. Don't forget about the rest of what was once Gondwana, a proud supercraton. Now it's separating into its constituent cratonic pieces. India, Australia, and Antarctica are finally starting to break apart. Australia and Antarctica have kind of had a thing for a long time, and they're going to hang out together for a while longer. But India is going to be the one that really cruises north, because you see it's on the other side of this mid-ocean ridge here. And so the Tethys plate here is being subducted, and that's going to be bringing India north over time. Well, in the latter part of the Cretaceous, okay, we have the severe orogeny still going on in western North America, subduction of the Farallon plate here, while this orogeny is going to transition into the fifth and final compressional orogeny for western North America, and it's called the Laramide. So this is the one that's going to form the Rocky Mountains. So it's going to begin at right about 80 million, the Laramide orogeny. Compressional tectonics on the west side of North America and South America. So continuation there. Continuation of the subduction-related orogenies over here in Southeast Asia. And the rifting continues. We have North Atlantic and South Atlantic. And the Indian Ocean is finally forming here in the south. Again, India is going to travel farther north as the Tethys Plate gets subducted. But notice Australia is ringed with mid-ocean ridges, so it's not really going anywhere. And that's the same for Antarctica. It's almost completely surrounded by mid-ocean ridges. Well, if we look at the Atlantic Ocean basin a little more closely, as rifting progresses, the margins of this ocean basin are passive margins. It's passive because there's no major active tectonics going on. The tectonics are the extensional tectonics of the mid-ocean ridge here. But as you create more plate and they separate out, these passive margins here develop and they mature over time with erosion of the continent. Those sediments are deposited on the margins on either side of this new ocean basin. With time, not only the ocean basin itself widens, but these passive margins mature and widen as well. During the Cretaceous, the North Atlantic was more of a wider ocean basin than a seaway now, and there's these broad continental shelves being deposited right on top of the edge of the continental part of the plate there. So this is all the North American plate. On the left, here's the Mid-Atlantic Ridge, and then this is all the Eurasian plate on the east side. Passive margins on either side. The South Atlantic is lagging behind a little bit, and it's more of a seaway, and its passive margins haven't had the time to accumulate the sediment that the North Atlantic has. Still passive margins. There's no subduction going on here, and this is the South American plate, and this would be Africa. So the Cretaceous would see an evolution of not only the ocean basins, but of their margins as well. In western North America, the severe orogeny is occurring throughout most of the Cretaceous. It's a subduction-related orogeny that involves folding, thrusting, and uplift. And here's a map of the western part of North America. The subduction zone itself off to the west. Line of volcanoes, which would be the continental arc that is being built on the North American continental plate. And then this is a line of thrust faults out in front of the arc off to the east. And this is the limit of the severe fold and thrust belt. Why this is happening is this plate over here in gray, that's an oceanic plate called the Farallon Plate, and it's subducting underneath North America, which is a continental plate. So in this diagram here, here's the Farallon Plate as it was in the Jurassic, subducting underneath North America, giving you this continental arc, which we talked about. During the Cretaceous, we actually see the same situation, the Farallon subducting down to the east underneath North America, but the angle at which it's going down is less. So it's more of a shallow angle. So from horizontal here, that's about a 45-degree angle maybe. While during the Cretaceous, it's a much less angle. Maybe it's 20 degrees. So it's a shallowing of the slab dip. So as this decreases, it's going to change some things. For one, there's going to be a little bit more coupling between the plates. And so more stress is transferred from the downgoing oceanic plate to the overriding continental plate. So more folding and thrusting. Where the downgoing plate goes through about 100 kilometers depth, that's where we see an area of melting above the plate, and those magmas will rise and form a continental volcanic arc. So with a configuration like this, the Farallon during the Jurassic is passing through 100 kilometers, maybe right here. Magmas rise and form volcanic arc here. But with time, the dip of the slab decreases, so it passes through that magical 100-kilometer depth farther east. Those magmas rise and erupt here, which is farther east from the subduction zone than it was before, and that's because of the shallowing of the dip of the Farallon plate. Okay, so the dip angle of the downgoing subducting plate actually has something to do with where the volcanic arc occurs on the overriding plate. The steeper the angle, the closer it is to the subduction zone. The more shallow the angle, the farther from the subduction zone. One last thing about the severe orogeny. This is a diagram here showing the contrast in tectonic style between the severe and then the later Laramide orogeny. The colored units here are all sedimentary rocks, and the gray unit is the Precambrian basement rock. And notice that all the folds and thrusts are in the uppermost sedimentary rocks. So fairly shallow level tectonics. Whereas in the Laramide, there was some of that going on too, but there were these big basement chord uplifts. So a different style that would involve the exposure of these deeper Precambrian basement rocks during the Laramide. Speaking of the Laramide, it would occur during the late Cretaceous and progress into the Cenozoic, into the early Tertiary. Where we left off with the severe, we had the subducting Farallon plate, and its dip angle was getting less and less. Well, during the Laramide orogeny, that would continue, and the dip angle would get very low, in fact, almost horizontal, very shallow subduction, so a flattening of the subduction angle. It means that there's a high degree of coupling between the downgoing plate and the overlying North American plate, so a lot of stress being transferred to the overlying plate. We're still getting folding and thrusting in parts of the plate, but now we're getting a different deep-seated kind of compressional uplift tectonics going on farther east, and that's what's going to make much of the Rocky Mountains. These Laramide style tectonic structures often involve high-angle reverse faults, and they are bringing up deeper, older Precambrian basement rocks. So you get these big Precambrian uplifts. Here's a cross-section through the Front Range in Colorado, and it shows the Precambrian basement rocks here, and these are the high-angle reverse faults, and it's basically uplifting these older rocks, exposing them. The hanging wall's moving up, and it's exposing this side here. This picture right here is reversed. With compression, you have the uplift. Here's the hanging wall moving up, exposing the Precambrian bedrock. So high-angle reverse faults, they're parts of the Rockies that are more severe, like more fold and thrust belt related, but the Colorado Rockies and down into New Mexico are more like this. With this flat subduction, it's affecting a large area of North America. The Rocky Mountains themselves extend to the east of what was the Farallon subduction zone. So this is the furthest extent tectonics has transgressed, if you will, into North America. It's because of this flat slab. And all the subduction that's gone on since the Antler and Sonoma and Nevada and Sevier, the plate has either been going off to the west or it's been more of a high angle down to the east. Now it's shallow off to the east, and so we're getting these stresses in the North American plate, which are creating mountains very far east into the craton. It's no longer just the margin being deformed, it's the actual craton itself being deformed. This is the area where the modern-day Rocky Mountains are going to form. Okay. Here is the modern-day Rocky Mountains there in the Front Range, the beautiful Flatirons, and this is Boulder, Colorado. But wait, there's more. So the Laramide orogeny affected portions of the North American craton that hadn't seen deformation in a very long time. This map right here shows the eastern limit of the severe fold and thrust belt. So pretty much present-day Nevada down through where Las Vegas is. East of that, though, this is the area that was affected by the Laramide orogeny, okay, with the flat subduction producing not just folds and thrusts, but high-angle reverse faults. So Arizona and this Four Corners region have a lot of very characteristic Laramide structures, and these are uplifts and basins and monoclines, world-class monoclines, in fact. There's a number of areas in Arizona and surrounding states where we see these Laramide features and structures, the Kaibab uplift, the Monument uplift, the Zuni uplift, the Defiance uplift. So these are areas where the rocks have been uplifted, and then intervening areas of downwarping basins. The Black Mesa Basin would be one of these. Different areas where we're seeing different types of structures forming. This is a map of northern Arizona showing the location of monoclines. Remember what a monocline is. It's a one-limb fold where you have layers flat on top, a warp, and then flat on the bottom. The arrows here show the direction of dip of the monocline. The long line is the trend along the monocline, and then the arrow points the direction it's dipping. So you can see all these monoclinal folds up here are dipping off to the east. Some of them are dipping off to the west, but they're mostly oriented such that the axis of the monocline is north-south. So the stresses would have been coming in from east-west. Right along the San Juan River, the Rapley monocline is outstanding. So this is how these monoclines formed during the Laramide orogeny. We have basement rock, and it's Proterozoic basement rock in this case. Proterozoic, Paleo, Meso, and Neo, X, Y, and Z. Overlain by a layer cake of Paleozoic and Mesozoic sedimentary rocks. And they're typically basement faults down there that were ancient, and they occurred back during the Proterozoic, but then they can become reactivated. Why break new rocks when you already have a break existing there? So some of these major Proterozoic faults were reactivated during the Laramide. One of these faults could be reactivated, and now this would be the hanging wall side, and it's uplifted. So you're getting movement up on the hanging wall side, and that's a reverse fault caused by tectonic compression. What happens in the beds above it is that they get offset. But faults don't go on forever, and they peter out a little bit as they go farther and farther up. And so deeper in the crust, the rocks are actually offset. Farther up, they're actually just folded. It's kind of like just a gentle warping on the surface versus down deep, they're actually offset. If you think of a rug with a piston underneath the rug, and the piston comes up, the rug will be warped above it, and the rug is the Paleozoic and Mesozoic rocks above that piston. So with time, after the orogeny is over, post-Laramide, we have erosion, and it's going to erode the hanging wall block down first because it's higher. So these rocks get eroded down and they disappear, and so you're eroding down into older rocks on this side, leaving some of those rocks over here on the other side. What we see today, for example, in the Kaibab upwarp, which is this one here, there's a monocline on the east side called the East Kaibab monocline. There's a major fault there called the Butte Fault, and it was a reverse fault with a west side up, and it warped the rocks like this. And today we see the Kaibab Plateau or the Kaibab Uplift on the west, and the Vermilion Cliffs, the younger rocks off to the east. Classic monocline geology in northern Arizona and southern Utah. Let's turn our attention to Cretaceous rocks, and a major rock type representing the Cretaceous are carbonate rocks, including those of the chalk group in Western Europe. So these are late Cretaceous to early Tertiary in age, and they represent deposition in warm, shallow seawater of the Tethys Ocean during the Cretaceous. Shallow marine limestones, tiny organisms with their calcareous shells forming chalk. As they die, they fall on the seafloor, and you have this calcareous sediment that actually has a name, coccolith biomicrite. And the coccolith is the small little shell, and biomicrite is microscopic limestone that's coming from a biological organism. So these types of carbonates here are very common on the southern coast of England. This shows the geologic map here, and they have been since deformed during the Alpine orogeny into, in this case, a broad anticline. And on the coast, these chalks are seen here. Very iconic rock formation. Another important Cretaceous rock type is black shale. Here's what black shale looks like. Typical black shale right here. dark in color because the iron in the shale is not oxidized significantly. An outcrop fairly distinctive. Here, interbedded with lighter colored carbonate rocks, so the limestones are lighter colored and the black shale is contrasting real nicely with its darker color. These different named limestones are age names: Aptian, Turonian, Cenomian. Those are Cretaceous names for ages. We find these black shales distributed around the world from North America, South America, Europe, and we think they occupied shallow marine environments in each of these places, whether it was the North American interior seaway or the Tethys Ocean, Western Europe. I think these black shales had their origin in shallow marine areas where there wasn't a whole lot of free oxygen in the water. So that means poor oceanic circulation, relatively stagnant, if you will. So the water is oxygen poor or anoxic. Whether the water is deep or shallow, if it's oxygen poor, it's anoxic. So let's look at this diagram here and see how conditions could develop so that we get these black shales. So here's a continental shelf, shallow marine environment, and here's a deeper ocean here. And when the water is well mixed, you get more oxygenated water, oxygen-rich water near the surface, mixing with deeper waters. So a lot of circulation, you'll get oxygen mixed throughout the whole water column there. But for various reasons, circulation patterns can change, and you won't get mixing between the upper and lower parts of the ocean. So the lower part becomes depleted in oxygen, thus more anoxic. This is the area where you can get black shales developing. So the mud will be deposited there just like usual, except the iron in that mud will not be combining with oxygen to give it a reddish color or something else. So it'll remain black like these samples we see here. What happens then is that if conditions change so that there is a marine transgression, sea level rises, okay, and that shallow continental shelf is then inundated with deeper and deeper water. Some of that anoxic deep ocean water then transgresses up onto the continental shelf, and its oxygen poor nature starts to allow the deposition of black shale on the continental shelf of these shallow inland seas. Upwelling of the anoxic deep water into these cratonic seas is what forms these black shales. Many of these represent ocean anoxic events. So these are periods during the Cretaceous where poor circulation in the oceans and that deposition of these shales. Okay, and we link these ocean anoxic events with not mass extinctions but lesser level extinction events, extinction pulses during the Cretaceous. Another major Cretaceous rock type, flood basalt of the Ontong Java Plateau. So this is a flood basalt eruption of the early Cretaceous, about 125 to 120. Here's a map of flood basalt on continents and in the ocean basins. All of them are considered large igneous provinces. So these lips include both continental flood basalts like the Siberian traps, the Deccan traps, Camp, and others, but also oceanic plateaus where the flood basalts erupted on an oceanic plate like Kerguelen here and the Ontong Java Plateau. A massive eruption of, we think, over 8 million cubic kilometers of mafic material erupted over the span of a few million years in the Western Pacific. This is like twice the volume of the Siberian traps, which gave us the biggest mass extinction of all time. There's no mass extinction related to this eruption though. And the main reason for that is the Siberian traps erupted on land where the gases, the carbon dioxides and the sulfur dioxides from the eruptions could go freely into the atmosphere directly. Whereas those same gases during this submarine eruption would go right into the ocean. So while not directly affecting the composition of the atmosphere, it would be directly affecting the composition of the ocean. This shows where we think it happened. a massive, probably mantle plume generated eruption like most flood basalts are, but in this case on oceanic plates, the Pacific, Farallon, and Phoenix plates. So this eruption, as I mentioned, didn't result in a mass extinction event, but there are other extinction events that occurred that were lesser. We call them extinction pulses. Still large numbers of organisms going extinct, but just not enough to qualify as a mass extinction, at least to the level of the Big Five in the Phanerozoic. This shows the Cretaceous, starting from early Cretaceous going towards late, and it shows a number of what we call ocean anoxic events, OAE. And these are events that likely saw the ocean basins depleted in oxygen for some reason. Circulation changed in the oceans, or the actual composition of the water changed so that there was less free oxygen. And there are a number of intervals during the Cretaceous where these would occur. And these are marked by extinction pulses in the fossil record. And we've labeled them here, ocean anoxic events. Some have different names, like Pharaoni and Selly and Pakir and various other ones. And some are just given unglamorous names like OAE-1A, OAE-1B, OAE-2. As it turns out, ocean anoxic event 1A, the Selly event, occurred at about 120. So it correlates really nicely with the Antang Java Plateau eruptions. So there's likely a correlation there between the flood basalts, the level of oxygen in the water giving you black shales, and then resulting in these extinction pulses. Well, another major flood basalt event occurred in the Cretaceous, and it's called the Deccan Traps, which occurred at the end of the Cretaceous and lasted into the early part of the Tertiary. 67 million down to 65 million, right across the KT boundary, as we call it, the Cretaceous Tertiary boundary. Notice the decimal points in the ages here, because this boundary and the ages of this flood basalt have been the attention of a lot of scientific study, and so the geochronology is very important to get it as precise as possible. We think this was an eruption of about 500,000 cubic kilometers of flood basalt, and compared to the Antang Java Plateau, this is only like 1/16th. If Antang Java was 8 million, this is just 500,000. So the difference here is this erupted mostly on a continental plate, and thus it's a continental flood basalt, which might have looked like this: fire fountaining, fissure eruptions, gases like carbon dioxide and sulfur dioxide going right into the atmosphere. This is a diagram which has a lot of information about the Deccan Traps. This is what they look like today. This is where they are exposed in India, mostly in the western portion of India, but there's a flow which extends for a long distance off towards the east side of India. This shows the dating, and there are three main pulses of this eruption. The first phase occurred before the KT boundary, which is right here at 66. So this phase 1, had started before the boundary. Phase 2 was where 80% or so of the volume was erupted right across the boundary. And then phase 3 followed in the Tertiary. So this whole eruption spanned the KT boundary there, where most of the volume was erupted right at the boundary. If you're looking at these, we're looking at polarity of the Earth's magnetic field from normal to reverse to normal. That's one way we can date rocks that have magnetic minerals in them, like basalts. So we use this magnetostratigraphy to figure out the different polarities, and we can correlate using that. But we can also directly date these rocks using uranium-lead isotopic system to get these very specific dates. And the whole point of that is to link these eruptions with the KT mass extinction, which occurred right here. So a massive phase 2 eruption really peaked at 66, and it's this main phase which correlates very nicely with the KT mass extinction, which is the fifth and final of the big five mass extinctions of the Phanerozoic. Let's talk about deposition in the seaway of western North America. Here's a map showing North America and the depositional patterns within the North American interior seaway of the Cretaceous. So there's different types of sediment deposited across the seaway. Along either margin is probably where we saw more sand. And as you go towards the middle of the basin, there's more muddy sediment and even carbonate. We can actually see the transgressive regressive cycle in a stratigraphic column, which shows near shore sandstones at the bottom, overlain by deeper water shale, overlain by deeper clear water carbonates. That would be marine transgression. From shallow water rocks overlain by deeper water rocks. And then as the seas drained off, you would see a regression, and you'd go from deeper water rocks to shallow water rocks. So indeed we see that sequence in western North America. This is what it might have looked like, the eastern shoreline here, a coastal plain, and the sea comes in, and marine transgression. So the Dakota sandstone, we think, is the first rock unit representing this rising sea level. It's a transgressive seaway unit. Okay, it's the one right down here, and it represents kind of a near shore sand, age of about 100 to 90 million. A little bit younger is the Mancos Shale. Beautiful Mancos Shale here at Factory Butte. And the Mancos is probably a deeper water marine shale. And then the Mesa Verde group above that, it's exposed at Black Mesa in Arizona. Here's some cliffs of Mesa Verde group. This represents regression that occurred afterward. So near shore marine to deeper water marine, and then the regression itself with the Mesa Verde group. The Mesa Verde group is the very top layer of Black Mesa. You can see it overlies the Mancos Shale here, and the Dakota sandstone is right underneath. So these three units in the upper part of Black Mesa represent the North American interior seaway. Well, a very important rock unit in western North America that is latest Cretaceous in age is the Hell Creek Formation. And it has been dated specifically at 66.8 to 66.0. At the end of the Cretaceous, the KT boundary is at 66.0. So this rock unit occupies a position right at the very end of the Cretaceous. So it's important not just for that, but also it's a very dinosaur-rich unit. When we look at outcrops like this, here is the Hell Creek in the bottom, K for Cretaceous, HC for Hell Creek. These sedimentary rocks contain lots of different dinosaur fossils. So we go upward in this outcrop. These are Paleogene rocks, tertiary rocks, no dinosaur fossils. So the KT boundary is right here. That boundary is the extinction boundary, the KT mass extinction. So studying these rocks of the Hell Creek here help us learn about what the dinosaurs are like right before the end. The different kinds of dinosaurs in there, it's a whole range of herbivores and carnivores. There's Ankylosaurus, Pachycephalosaurus, there's Triceratops, there's Edmontosaurus, Tyrannosaurus, Ankylosaurus, Dakotaraptor. There are pterosaurs like Quetzalcoatlus and various crocodile forms. So a huge diversity of different dinosaurs. But when we look more closely at their distribution within the Hell Creek, you can see some interesting things. In the lower parts of the formation, there's all different kinds of dinosaur types. Blue here represents Triceratops, red the Tyrannosaurs, yellow are these Edmontosaurus. The remainder are some of these other types. As we move upward in the formation, we can see pretty much Triceratops and Tyrannosaurs remain about the same. There's an increase in the amount of these Edmontosaurus and a decrease of the other ones. With time, Triceratops becomes more abundant, so that by the time we get to the upper part of the Hell Creek, Triceratops represents almost 3/4 of the fossils found in the unit. A lesser amount of tyrannosaurs and admonosaurs, and you notice a disappearance of just about everything else. So a change in the dinosaur ecosystem in the Hell Creek Formation up towards this KT boundary mass extinction. That's the real importance of the Hell Creek Formation. Some other important rock types in western North America include ore deposits. So these aren't necessarily individual rock formations, but they're ore deposits in different locations across western North America that were developed during the Cretaceous. If we look at the tectonic picture here, we had a subducting slab, magmas coming up off the slab, lots of fluids coming off the slab, causing melting. These magmas would rise into the North American plate. The hydrothermal fluids associated with these magmas, as they moved through the North American plate, would take elements with them, and you would get formation of various ore deposits. There's different kinds of ore deposits depending on different factors. You can have these hydrothermal fluids injecting along fractures, and then as they cool, you'll get deposition of various minerals and various elements, so gold and copper and silver, and in vein deposits. Versus other types of elements might be distributed more continuously throughout the surrounding rock. So the hydrothermal fluids are disseminating through the surrounding wall rock and then depositing their elements in a much larger volume of rock. And these are called disseminated ore deposits. And so each of these occurrences are present in these ore deposits in western North America, both vein deposits, which we mine with underground mining techniques, and disseminated ore deposits, where it's much lower grade, much lower percentage. We have to mine those with open pit methods, much more bulk rock mining. Okay, so these are very important ore deposits for things like copper and gold. These are actually called porphyry copper deposits. Porphyry for the name of the rock that they're associated with. Porphyry is remember, it's an igneous texture, big and little crystals. Okay, porphyritic. Copper deposits, meaning copper is the main ore metal. So porphyry copper deposits across Arizona are very important, including at Morenci, which is the biggest porphyry copper deposit of them all. Morenci and several others form a major set of porphyry copper mines across Arizona, and it's one reason why in our state flag we have a star which is copper colored. Copper, cotton, cattle, and other stuff. So copper is major for Arizona, and one reason why are these Cretaceous igneous deposits. The climate of the Cretaceous was warm, tropical, subtropical, continuation warm climate from the Jurassic. No ice present on the planet. Certainly not the extreme hothouse environment of the Permian and Triassic. So we've seen this kind of warm climate several times in the Cambrian and Ordovician, in the Devonian, the Permian and Triassic, and now to a lesser extent at the end of the Cretaceous. We see kind of a warming through the Cretaceous. It culminates in a warm environment right at the end, and that would continue into the Cenozoic era itself. And then a broad, somewhat drastic cooling cycle all the way down to where we are today. This is interpreted from various rocks, again around the planet, which represent different climate zones. Coal would represent a coal swamp, which is more tropical or subtropical. Evaporites would be more arid. Glacial tillites would be more Arctic. What we can put together for the Cretaceous is that it was warm, but not extreme. Earth has definitely seen worse climates. Cretaceous life is just about everything. Animal life, if we're looking again at the amniote phylogenetic tree, the synapsids, the mammal-like reptiles, most of those have gone extinct except for mammals. Mammals are present throughout the Cretaceous. On the diapsid side, we have the different types of squamata, lizards and snakes. Archosaurs like crocodiles, pterosaurs, dinosaurs, birds of all different kinds, all present during the Cretaceous. Pterosaurs like Pteranodon. Ooh, look at Deinosuchus, huge crocodilian form there, going after T-Rex with its two-fingered hand. Here's a giant mosasaur, marine reptile, going after a shark. Pretty good diversity in the Cretaceous of animal life. Well, let's start with land vertebrates, the dinosaurs, of course. So our ideas of dinosaur life have really changed over the years, and much of it's due to the work of people like Dr. Bob Bacher. And our old conceptions of slow, sluggish, cold-blooded beasts has changed, and with much discussion, to a different conception of how we think dinosaurs lived. And so some of these would include the fact that they grew very rapidly, from meager beginnings to huge, massive forms. We think that they actually might have had active lifestyles. And to do that, they would have required a metabolism that was different than our previous thought of what dinosaurs lived like. They would have had to have been warm-blooded in many cases. So it changed our conception. We think now that dinosaurs were warm-blooded and not the cold-blooded, sluggish beasts of the past. We also think many of them might have had feathers. Many of them walked upright versus being propped up on their tail. All sorts of different conceptions of the past have been busted over time by ongoing science, much of it done under somewhat hostile conditions. So a lot of props to Dr. Bob there. We think that some of them actually lived near the poles. We find dinosaur remains at high latitudes, including Antarctica. There are indications that these regions were ice-free, and they were relatively cool areas, though, pretty much dominated by forests. And in those forests lived dinosaurs. Another aspect of dinosaurs is we think they really developed and changed quickly. So their rate of speciation was fairly rapid, and they evolved quickly, and that's why we see so many different forms and types. So all of this is explained in the seminal book written by Dr. Bacher back in the 80s, and it was called The Dinosaur Heresies. And in this book are his ideas where he's challenging the orthodoxy of what dinosaurs were like. A true heretic, Dr. Bacher. There are different types of dinosaurs. One major group were called theropods. Theropods technically had 3 toes. So there are many different kinds of theropods. Which one do you want to talk about first? Yeah, Tyrannosaurus. So the Tyrannosauridae. This is a family of all different Tyrannosaurus rex-like creatures. And this diagram here shows the phylogenetic tree of family Tyrannosauridae. Tyrannosaurs, and that's the way I usually call them, is tyrannosaurs, because that includes all these different forms, not just Tyrannosaurus rex. Tyrannosauridae, the family, has Albertosauri and Tyrannosaurini. And of the Albertosaurs, there's Albertosaurus and Gorgosaurus. And of the Tyrannosaurini, there's Tyrannosaurus, Tarbosaurus, Daspletosaurus, all these different ones. One thing is that they didn't all live at the same time. Some were present earlier than others. All of these species were present in the late Cretaceous, but it was really only Tyrannosaurus present right at the end. Albertosaurus made it close, but Tyrannosaurus rex was there at the end. You can see here compared to each other. Okay, the Gorgosaurus is the smaller one, and these Tyrannosaurs over here are all these other forms, and they all look pretty similar, except some are bigger than others. Daspletosaurus, Albertosaurus, Tarbosaurus, and then finally T-Rex, the king. Okay, and pretty much lived right at the end, 66 to about 68 million. That was T-Rex. Hail to the king, baby. Another popular theropod dinosaur are the dromaeosaurs. Okay, and this is kind of a strange word for the raptors. Here's the phylogeny of Dromaeosauridae. and there are many different kinds, but they're all similar form. Velociraptor, Deinonychus, Utah raptor, Dakota raptor, all these different dromaeosaurs. They're all agile, bipedal theropods, had feathers, had the distinctive foot claw. They were dominant during the late Cretaceous up until the end, like Tyrannosaurus rex. They might have been around much earlier, actually into the Jurassic, but again, their dominance was in the Cretaceous. These forms have very close resemblance to birds. They're the type of theropods from which the birds have the closest relation. So birds and dromaeosaurs are very close. Each one has characteristics of the other. Okay, so dromaeosaurs have very bird-like characteristics, feathers being one of the most obvious. Of these raptors, many of them look actually like some of the large so-called terror birds of the Cenozoic, very similar to these raptors. The main difference is these are reptiles, the birds are not. So while the birds evolved from these dromaeosaur theropods, they are not reptiles. All of these had similar characteristics of the feathers to various extent, to the claw and all that. Some were very large, including Utah raptor, very large. Deinonychus was very large too. Velociraptor, probably not as large, probably smaller, and given its name, a more swift and speedy raptor. Another major group of lizard-hipped or saurischian dinosaurs were the sauropods, and these were the largest land vertebrates to ever live, from Diplodocus to Brachiosaurus and others. Compared to humans, you can see the relations compared to giraffe and elephants, rhinoceros, and even some strange Cenozoic forms we haven't seen yet, which were the biggest mammals ever to live on land. While the Saurischia, or lizard-hipped dinosaurs, was an order including the theropods and the sauropods, the bird-hipped, or ornithischians, include a whole diverse suite of other dinosaurs. So this order included guys like this ankylosaur. So the ankylosaurs lived from just in the late Jurassic, but all through the Cretaceous right to the very end. And these were armored herbivores, Ankylosaurus here. The hadrosaurs, the duck-billed dinosaurs, the cows of the Cretaceous. These are really abundant in the later part of the Cretaceous, and they occupied all different environments, and we see their fossils in many places. There's ceratopsians. These would also be in abundance throughout much of the Cretaceous, especially the latter part, and these were the horned and frilled herbivores like Triceratops. Well, we could talk about dinosaurs all day, but we've got to move on, and they're always pterosaurs, air vertebrates. So these are flying reptiles that have been around previous to the Cretaceous, and they continue right up until the end. And these include some of the largest pterosaur forms ever, the largest vertebrates ever to take wing and fly. And so some of them are shown here with relation in size to a human. Some are very small, like Patinosaurus, almost like a bat-sized creature. Some are very weird with various head appendages, like Tapagera here. Some have a bony crest on the backside, unlike the pterodactyls. Pteranodon has the characteristic point on the backside of the skull there. They were a little bit larger. And the largest ones, Quetzalcoatlus northropi here, lived right at the end. Huge form, which might be exceeded by one other type of pterosaur, but these were truly the giants of the skies. Again, when these would land, how would they walk around? And so they did walk around probably on 4 limbs. And remember, their arms are right here, and their arms are connected to their legs with this membrane here, which is their wing. Hollow bones allowed something this big to fly. And when they landed, they were probably somewhat awkward, somewhat vulnerable, but they did have the ability to walk around, and Quetzalcoatlus probably was a similar size to a giraffe. So as much as we want to talk about dinosaurs and pterosaurs, we have to talk about marine vertebrates, specifically marine reptiles, because they really flourished in the Cretaceous. And there are many different forms. The plesiosaurs have been around since the earlier parts of the Mesozoic, from 204 all the way to the end at 66. And one form of plesiosaur is Elasmosaurus. And you can see the long, typically long neck, small head, paddle-like limbs of a plesiosaur. There are also other types of this order that are a little bit different. They have large heads, big jaws, very short necks, still with the paddle-like limbs. And so pliosaurs were very common during this whole time as well. And they would go extinct not at the very end, but during one of these ocean anoxic events, specifically number 2. So here is what we think the largest of them was, Kronosaurus, possibly about 10 meters in length. And so it lived around 120 to 100 in the Cretaceous. And finally, the ichthyosaurs. And they've been around since the very beginning of the Mesozoic. You'd see a whole bunch of different forms. It all go extinct just before the end of the Cretaceous at about 90 million. The real king of marine reptiles in the Cretaceous was the mosasaur. So mosasaurs were dominant in the latter part of the Cretaceous. These sea monsters got to huge sizes, and their various types. They more or less had a tail that was kind of eel-like. Tylosaurus proriger was a huge mosasaur, and these would be present from about 100 million years ago down to the end at 66. And this diagram here shows the extent of the ichthyosaurs and plesiosaurs and mosasaurs with time. Some of them went extinct before others. The elasmosaurs and the mosasaurs were there at the end, whereas the ichthyosaurs and others were not. Our discussion of marine reptiles wouldn't be complete unless we talk about Archelon, the largest sea turtle ever. Here's the typical Guinness Book of World Records picture of the fossilized skeleton of Archelon. Huge sea turtle, maybe 5 meters in length. Well, what other marine vertebrates are there? Well, yeah, the fishes. There are many different kinds, and to pick one large predator was Xiphactinus. In fact, here we have Xiphactinus audax, which might have gotten to a size of 6 meters in length or so. And so we can see it here compared to a human. These had a big, menacing front end. In this artist's reconstruction, even going after a pterosaur. The fish were even menacing back in the Cretaceous. Xiphactinus lived right up until the end as well. Well, other forms of fishes included the sharks, as always, predators. And there are many different kinds in the Cretaceous seas, big ones and small ones. Cretoxyrena mentelli was a big one that lived until about 73 million years ago. Hybotus is a very common, successful shark form during the Cretaceous. It was actually present all the way back into the Paleozoic, 260, that's Permian, and lasted all the way to 66 million. So it's a very successful fish. Well, let's talk about some marine invertebrates here. And I'm going to stick up for the little guy, okay, because we've been talking about all these big creatures now. And so the organisms that form the deep sea sediments that are common in the Cretaceous oceans, one group are the diatoms and radiolarians. And these are microscopic organisms which extract silica from the seawater and then use that to excrete a shell, which is made of silica. And when they die, they float down to the bottom, litter the seafloor with very fine-grained sediment that is very silica-rich, and we call that siliceous ooze. which then crystallizes to form the very fine-grained rock type chert. Okay, and so we see siliceous ooze being deposited. That's the green areas here. Various regions around the world. Here's a bunch of diatoms. That's 10 micrometers in size. It's very small. The other major kind of sediment is calcareous. Calcareous ooze would be the collection of very small microscopic skeletons of organisms like calcareous nanoplankton and foraminifera. These organisms extract calcium carbonate from the seawater and excrete it to make a calcareous shell, and when they die, they litter the seafloor, becomes a calcareous ooze, which then crystallizes into the sedimentary rock limestone. So two major types of sedimentary rock, chert and limestone, form from these microscopic creatures. Again, this is a microscopic view, 8 micrometers. Look at that beautiful detail, little flowers on there. And then here's a foram, different creatures. And then calcareous ooze is typically deposited at or around the equator and in the middle latitudes, and typically at more shallow water depths, maybe a few thousand meters, versus deep ocean basins. These are two types of organisms which create two very common rock types. Let's summarize life in the Cretaceous seas by looking at the Western Interior Seaway, or the North American Interior Seaway. This diagram here shows the diversity of all the different forms, many of them marine reptiles, some of them fish, some of them invertebrates. With human for scale here, mosasaurs were very large. Tylosaurus proriger is the largest one. You can note the mosasaur's tail has a distinctive larger down fin. So these mosasaurs are all different forms, but Tylosaurus proriger is the big one there. Of course, there were plesiosaurs like Elasmosaurus and others that would also be present. There was Archelon, the giant sea turtle. Giant sharks like Cretaceous mentelli. Also the bulldog fish, Xiphactinus audax. Not only were these vertebrates present, but also invertebrates like the cephalopods, the ammonites here, which had straight-shelled versions like this guy here, that's Baculites. All of these would constitute what Nigel Marven would call Hell's Aquarium. And a couple other artists' renditions of life in the interior seaway, very exciting. Cretaceous mantelli taking a piece out of a tylosaur with pterosaurs looking on, and then Elasmosaurus down in the shallows looking for food, along with, it's probably a shark given the tail here. Well, last but certainly not least, the land plants, and now we finally get to talk about flowering plants, or the angiosperms. So the first flowering plants would occur in the Cretaceous as early as about 125, and a few million years later they would become widespread. So on the geologic age range diagram, we've seen the rise of the spore plants in the Paleozoic, and then the seed ferns would come along as well, and then late in the Paleozoic, the gymnosperms. Not until the very end of the Mesozoic before we get to the angiosperms, the flowering plants, and they have been proliferating ever since. The earliest fossilized angiosperm is Archaeofructus, and this is about 125, and that's the first one we're really clear on. Magnolias would appear at about 100 million, and they've been around ever since. So these replace conifers as the dominant tree anywhere at 60 to 100 million years ago. So the flowering plants are the ones that are really expanding while the other forms are decreasing. The end of the Cretaceous would see a mass extinction event, one of the big five of the Phanerozoic. Looking at the chart here, we can see the progression of biodiversity throughout the Phanerozoic, starting at the beginning of the Paleozoic and ending right now. diversity of life has been increasing pretty much ever since that Permo-Triassic mass extinction. Okay, we can see several deviations in the diversity, and the biggest ones are the big five mass extinctions. The one at the end of the Ordovician and Devonian, the Permo-Triassic mass extinction, the one at the end of the Triassic, and finally the one at the end of the Cretaceous. This one is usually referred to as the KT mass extinction or the KPG mass extinction because it occurs at the boundary between those two periods. We used to talk in terms of the tertiary, which is the Neogene and Paleogene, so KT, but we've been using Paleogene and Neogene more now instead of tertiary, so it's just two different ways to call it the same thing. So end Cretaceous mass extinction. And you can see in terms of genera here, it's a fairly significant drop of maybe a little less than half of genera on the planet going extinct, which is similar in magnitude to the end Triassic and some of the other ones, but not quite to the extent of the huge wholesale die-off at the end of the Permian. Many creatures were affected by this, of course, including almost everything we just talked about. Dinosaurs, all of them. Pterosaurs, all of them. Most marine reptiles, many different kinds of plants. So a lot of different species affected. The real interesting part is how some creatures survived this mass extinction when other ones didn't. And that's a question that puzzled us for a long time, and some of them have easier answers and some will never answer. The cause of this mass extinction is at least twofold. One, we have evidence for a major flood basalt eruption right at the boundary. It actually started before the boundary. The major pulse was across the boundary and then continued after. And this was the Deccan Traps, a terrestrial cause, but then also an extraterrestrial cause, possibly a large impact event we think could have caused major disruption of ecosystems based on not just the blast effect and the heat and all that, but the blocking of solar radiation from the impact debris. So over years, an impact winter could have ensued. There's certainly evidence for both and other explanations as well. So at least two major mechanisms here operating to produce this mass extinction, if not more.